Okay, so here's another PE HVAC question. The question states, the pump circulates water from the chiller to a network of fan coil units in a closed loop. The effect of all minor losses due to fittings, tees, valves, fan coil units, and the chiller, as well as the friction losses in straight pipe, are captured by an equivalent length of 2,500 feet and a Darcy friction factor of 0.025. If the pump mechanical efficiency is 80%, the brake power for the pump is most nearly what? So the first thing we need to do is to get the pump power. So if we go to our handbook and search by pump power, we'll get the brake horsepower equation, which is this guy here. So if I copy that over and bring it in, we can see that our brake horsepower for our pump depends on the GPM, the change in head across the pump, specific gravity, which we'll just say is 1 in this case, and then our pump efficiency. So we're given this guy, and we need to find delta H and the GPM. Well, the GPM we can find pretty quickly by using the chiller tonnage and the change in temperature across the chiller. So if we use this equation, Q equals 500 GPM delta T of water. We know that the chiller is a 20-ton chiller, so 20 tons times 12,000 BTUH per ton equals 500 GPM, and then the change in temperature is 54 minus 44. So 54 minus 44. And I'm going to put that into my calculator here. 20,000 times 12. So we're left with 48 GPM. So that's our flow rate. So now we need to find delta H here. And if we go to our handbook and search Moody, we get the Darcy-Weisbach equation, which calculates the friction head. So we're going to grab this guy. And there's also one other thing we need to grab from the handbook, and that's going to be the diameter and the area of the pipe. So this is a Schedule 40 2.5 nominal inch pipe. This 2.5 inch doesn't necessarily mean that that's what the pipe is. Like, that's not the actual diameter of the pipe. These are nominal sizes. So we need to go to our handbook and search Schedule 40. Search. So you can see we have 2.5, but our inside diameter is actually 2.469. So it's not quite exact, but close enough, really. So we're going to grab this guy, bring it in here, shrink that down. Okay. So for this equation, we're given this. This is the friction factor. We know the length. That's the equivalent length of 2,500 feet. The diameter is going to be this inside diameter here. And we need to find V squared, or V. So we can find the velocity from the GPM that we just calculated here. So if we have 48 gallons per minute, we need to convert that to feet per second, because we know that this gravity is in feet per second squared. So we also need this to feet per second to match. So we know that 1 minute, 60 seconds in a minute. And now we need to convert gallons to cubic feet. If you go to our PE handbook and then go to engineering terms and symbols, we'll find that 1 gallon equals 0.134 cubic feet. So 1 gallon equals 0.134 cubic feet. And then we also need this in foot per second, so we need to divide by an area. So we're going to use this flow area here, this guy. So we're going to divide by 4.785. And notice that this is in inches squared. And we're in feet cubed here. So we need to convert that inches to cubic feet. So we have 12 inches squared equals 1 foot squared. Okay. So I think that's all we need right now. So I'm going to go ahead and put that in my calculator. (48) divided by 60 times 0.134 divided by 4.785 times 12 squared. So we're left with 3.226 feet per second. Okay. So we have everything we need to find this friction head. So we're going to go ahead and plug these in. So HF equals friction factor is 0.025 times the equivalent length, 2,500 feet, divided by diameter, which is 2.469. That is in inches, so we need to convert that to foot. So 12 inches and 1 feet times 3.226 squared divided by 2 times gravity, 32.2. So I'm going to put that into my calculator. 0.025 times 2500 divided by 2.469 times 12 times 3.226 squared divided by 2 divided by 32.2. So we are left with 49 foot of head. So that's our friction loss. That's what our pump needs to overcome. So if we go back to our brake horsepower equation, now we have everything we need to calculate this. So brake horsepower equals 48 GPM times 49 times 1 times 3960, and our efficiency is 80%. So 0.80. Plug that in my calculator. We have 48 times 49 divided by 3960 divided by 0.80. So this leaves us with 0.74. And that is our brake horsepower of the pump that we need. So that is our answer.